So far, we have primarily studied uniform probability. So in uniform probability, every outcome has the same likelihood. And that gave us this really nice formula for calculating the probability of an event. Just calculate the cardinality of the event, the number of outcomes that are contained in it, and compare that to the size of the sample space, and then you will know the probability. Now, here, we are going to consider what happens when we are outside that context. We're doing non-uniform probability now. And so what we're going to do is we're going to take some of our intuitions and ideas that we built up for uniform probability, and we're going to import most of them to this more general setting. So here's what we're going to do. We're going to say, hey, I have a sample space again, and my sample space is full of outcomes. What I need to do is I need a probability measure, and what my probability measure is going to do is it is going to be a function that takes events. So an event is a set of outcomes, which also means it's an element of the power set of S. So this here, so this is the power set, is the set of all events on S. And what I need to do is I need to say something about how this function works. So here's how it works. It has three properties. So first of all, probabilities are never negative. Probabilities are never negative. So whatever my method for assigning probabilities is, it's always the case that the probability is greater than or equal to 0 for any event in my sample space. Furthermore, I have a second property. I'm going to have three in total. My second property is disjoint additivity. So it must be the case that the probability of A and B is equal to the probability of A plus the probability of B if and only if A and B are disjoint. So my idea from before that I was able to state as a theorem is now part of the definition. I say, hey, whatever my method of assigning probabilities is, it must be the case that if and only if A and B are disjoint, I'm allowed to compute the probability of a union by adding the probabilities of the components. And then finally, if I ask myself, hey, what's the probability of the event S, the sample space itself? You can think of that as the probability of something happening. Guess what? The probability of something happening has to be equal to 1. So probabilities still have to add up to 1. The probability of the entire universe of possible events has to be 1. So this is going to actually define a probability structure for us. And we're going to be able to use all of our familiar rules except one. It's no longer the case that I can calculate the probability of an event by just calculating the cardinality of the event and comparing it to the cardinality of the sample space. I need to look more closely at the specific rules that tell me how my outcomes occur. So here's the thing, and this is quite important. If I can't do this, I need to look really carefully at the structure of the problem, because the probability function that I have is going to be always quite different depending on exactly how the problem is set up. So let's do a few examples here. Suppose that I flip 3 independent weighted coins. So what weighted means is that the probability of heads is equal to some number p that I don't necessarily know. And this doesn't have to be 1/2 anymore. So these coins might be what are also called bent or crooked coins. Maybe the probability of heads is equal to 75% or 90%. So if I'm flipping these coins, I don't have uniform probability anymore because the probability of heads is not equal to the probability of tails necessarily. The outcomes no longer all have the same probability. Let's take a look and see what's in our sample space. So if there are three coins, well, then I have 2 cubed, which is 8 possibilities. And so if I start listing them out, I could have HHH, that's 3 heads. I could have HHT, that's 2 heads in that order. I could have HTH, which is 2 heads in a different order. Then I could also have a few other things. Here's HTT, 2 tails. I could have THH, that's 2 heads again, different order. I could have THT. I could have TTH, and I could have TTT. Okay, so there's all 8 things in my sample space. Now, question, what are the probabilities of each of these events? So if I was doing uniform probability, they would all have probability equal to 1/8, but that's not where we are anymore. We're just a little more sophisticated. What's going on? Okay, so I need to look now at the probability of heads, 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 and what's really important here is that I said independent. If I did not say that the coins were independent, we'd have to do something else. But here, I said that the coins are independent, and so because they're independent, I can multiply. So I know that the probability that the first coin is equal to heads, that probability is P. The probability the second coin is equal to heads is also P, and because I have independence, I can multiply. And so the probability of 3 heads is equal to P cubed. Again, I do not know what P is. I don't have to know what P is, but I know the probability of 3 heads is equal to P cubed. Okay, going down to HHT, I had to get 2 heads, so that's P times P. And then I had 1 tails. Tails occurs with probability 1 minus P. How do I know? Because the probability of heads plus the probability of tails has to add up to 1, which means that the probability of tails is equal to 1 minus the probability of heads. Okay, same calculation here actually. So P times 1 minus P times P. Let's just start, I'm going to start writing these in simplified form. So this is going to be P squared 1 minus P itself. Here HTT, so that's 2 heads and 1 tails. Or sorry, no, I made a little whoopsie here. That is 1 heads and 2 tails. So I have to square the 1 minus P. Tails, heads, heads. So 1 minus P times P squared. Tails, heads, tails. So that's P 1 minus P squared. I have another P 1 minus P squared. And then I have 1 minus P cubed. And then so here I was able to calculate all of these separate probabilities. And we could actually check if we wanted to see that all of these add up to 1, which satisfies this probability here. We need to make sure that the probability of the entire sample space adds up to 1. It's a little bit tedious to actually do that algebraic verification, but you can actually check, yeah, all of these, if I add them up together, add up to 1. So non-uniform probability allows us to move just farther beyond the setting of uniform probability. We can consider more kinds of events. We don't have to restrict ourselves to events where every different kind of component outcome is equally likely. We can consider a more complicated sets of problems where we can reason about the probabilities of different outcomes by using ideas related to, hey, first of all, I'm going to let my probabilities be arbitrary numbers, and then I'm going to compose them. I'm going to add them together or multiply them together. I'm going to use my rules in order to construct the probability of more complicated events out of simple building blocks. We will practice much more with this quite soon.